And okay, so today is we're going to continue our discussion of the model for Bayesian inference for a proportion. And let me, oops, trying to bring out the slides. What's happening here? Okay, give me a second. Okay, yes. All right, so last time, if you remember what we did, yeah, I think we were, oh, someone is here. Can you hear us? Hello? Can you hear us?
Definitely not.
Hello? Let's see. I think that was it. Oh, hello?
Hi.
Hi, can you hear us?
Yep. Mm-hmm.
This is awkward. Hello? Yeah, let me, sorry guys, I don't know why sometimes this, hello, can you hear us? Hello? Oh, okay, that's good. Okay, sorry for that. Thank you. I will start the lecture. Thank you for confirmation. All right. Okay. I mean, if you want to see yourself, okay, I will do it. Okay, let's, all right. So this is where we left last time. So let me give you a quick recap of what we did last time. So for this lecture of Bayesian inference for a proportion, I think we started with the Tokyo Express example that we thought about how to help the owner to sharpen his belief about whether people going to choose Friday to be the day to dine out during the week. So that is the question at hand. So we started with the discrete prior. If you remember what we did, we're trying to specify a list of possible values of the true proportion P. And then we come up with a list of probabilities associated with that list of values. And then it was a discrete prior because you have a limited number, like a fixed number of possible values for P. And then we realize, even though we can do this Bayesian inference through Bayes' rule, we realize that some of the limitation of the discrete priors, for example, if you didn't specify a particular value for the proportion P, you will never show up in the posterior because of the way that Bayes' rule is computed. And then that sort of like eliminate the possibilities of even having that number at all. So then we move to the thought about, okay, how about we can specify a continuous distribution for P? And we know that P is a proportion, so P should be between 0 and 1. So that's where I started introducing this beta distribution, which is continuous, has a PDF I introduced earlier, which is actually right now in the middle for a particular beta, right? With 3.06 and 2.56 as the two parameters. And then this is the PDF, and then this integrates to 1. It's a proper prior distribution. So then we started doing Bayesian inference for this continuous prior. So what we did, I think we looked at how beta distribution can be used to describe your prior belief. We talked about the beta select function. If you have two quantiles of interest that you can specify, then you'll be able to come up with a beta prior distribution to represent your belief. And then for the data part, which is the likelihood, again, we're using the binomial likelihood, the data model. So we again, so that's this part, remember. So again, likelihood function is the function in terms of the unknown parameter. Okay, you express it in that way. And then for our particular data, 12 out of 20, that's the likelihood. Okay, and then we stopped here last time, and now we're going to continue here to talk about how to derive the posterior distribution based on the prior of P to be a beta and the likelihood of P to be a binomial. Okay, so we stopped here, and I hope some of you got the chance over the weekend to look at it, how to do it. And I would say okay, so let me give you one more minute to catch up with what we did here. And one more thing is about this proportional sign. Remember last time I was saying that because the posterior distribution is a function of P, right? So anything that is not relevant to P is going to be a constant. So you're able to throw them away or throw them into this proportional sign. So if you look at what's in the prior distribution, you look at this is related to P, right? Related to P for sure. This, again, it's a beta function. We know that it's a constant in terms of P. So this can go into the proportional sign, okay? And then in the likelihood, so remember, once again, I just want to emphasize, we express the likelihood as a function of the unknown parameter. So this is the way to do it. And this, again, this choose function, it's a bunch of factorial computation that you're going to do, and then it's independent of P, right? So this, again, becomes constant, right? So that's why I was saying, well, if our goal is try to derive a posterior distribution in terms of P only, and then we're allowed to use this proportional sign, we only need to collect the terms related to P in the prior and in the likelihood, okay? So that's why I said last time, and pretty much starting from now, these are the portions that you should focus on when you're doing your derivation of the posterior, okay? So let me just stop for, pause for like 1 to 2 minutes and ask you to, obviously we talked about the beta distribution previously, like the kernel is very similar to the binomial, and that means also the kernel of binomial is very similar to the beta. So if you can collect the terms about P of the powers, and then also about the power of 1 minus P, you'll be able to recognize something in the same format, but with a different power, okay? And then keep in mind that we already started saying that beta is a conjugate prior for the binomial likelihood. That means once you come to a posterior term, which has P raised to some power and 1 minus P raised to some other power, try to link that into some beta distribution that you can try to think of, okay? So that's my hint for this part. So let me just stop for 1 to 2 minutes, and I will ask you just try to do it on your scratch paper or notebook to make sure that you know the general procedure of this. And this, again, it's mostly about algebra at this moment, okay? So try it. Maybe some of you tried it before over the weekend already. That would be good. If not, now is the time to do it really quick, and then I will show you the derivation, okay? So take your time, and I will start talking in about 2 minutes. Okay, so I now get to the next slide, and this is what I did, and I will pause for 1 more minute to let you verify the steps, and can see I have some comments of, yeah, I keep everything to start with, but then I drop the constants. Then I start to introduce the proportional signs. And then I combine the powers, so then I get to a posterior distribution that is in terms of p and 1 minus p with different powers. Notice in equation 18, when I wrote it, I didn't, so when I combined the powers, I actually didn't get the -1 altogether. So I keep it as 15.6 minus 1 is the power for p, and then the other also in terms of -1 for the power of 1 minus p. That's mostly because later, as you can see at the bottom of the slide, that we're going to try to use these two powers to recognize it as a beta distribution. And because the beta PDF have that kind of special setup, I should say, like the way that the powers are expressed. So I kept the -1 to help us to recognize later, okay? So let me, yeah, I'll wait for 30 seconds more so you can verify and then convince yourself that this is actually correct. Sounds good? Everybody is okay with this? Okay, cool. So this means, I said at the end, that if we can see the posterior is expressed in the kernel of P in this way, then we're able to jump to the conclusion that it is a beta distribution. It is another beta, okay? And the way that we recognize the beta is by looking at the power. So this is my new A, and this is my new B if I start with A and B, okay? So, and then I can directly just get those two numbers as the two new parameters for the beta posterior, okay? So there is some like hand wavy thing right now, as you can see that we were using, well, proportional and now proportional, and how can you convince yourself that even if now we're only left with the proportional, we're able to arrive at a beta. Okay, so this, I will talk about it after I finish part of this lecture. We're gonna do a derivation exercise, and then that's where the integration, I mean, your calculus knowledge will come into play, and I'll give you some hint. But for now, let's just convince ourselves to accept the knowledge that if you start with the beta, in here is start with the beta 3.06 and 2.56 as the two parameters, and then you combine with your 12 out of 20 as your data, and then you arrive at a new beta distribution with 15.6 and 10.56 as the two parameters, okay? So this is a known distribution. So remember, last time we looked at how you can like plot beta distribution, how you can look at many different types of beta distributions with different parameters. So now you know the posterior is an exact distribution that you know about, then you're able to summarize the distribution in various ways. Okay, so for example, now I want to know the posterior average of this P proportion, then I can just do it because I know it's a beta distribution, right? I can also do like a 90% credible interval covering the truth. You can use the Q beta function in R that's returning the quantile. So you can do various things. And then that's the beauty of having a conjugate prior, because when you start with something, you combine with the data, you arrive at a different distribution, but it's from the same family. And then because that distribution is known, it makes your life much easier to explain and then to summarize the posterior, okay? All right, so this is the gist, and let's see, with this in mind, what kind of lessons we can learn. So this is a more general setup. So earlier we're specifically talking about fixed numbers of A and B and then N and P. The most generic setup over here is if you have a beta distribution that's the prior beta AB for a proportion P, and then we have a general binomial NP for the data, which is what we call the sampling density, and then we get the likelihood function from it. Then the posterior distribution, notice how we typically write, because posterior is the unknown parameter given the data, okay? And then the most generic setup over here, if you start with AB, MP, then you're gonna come up with A posterior, that you have beta A plus Y, and then B plus N minus Y, okay? And soonish, we're gonna derive the exact distribution, I mean posterior, keeping the constants using this generic setup. This is the general setup, and I want to show you, sometimes people like to show a table like this in a way that how to look at the different sources about information of the unknown parameter, okay? So we know that one source is from the prior, okay? And the prior is a beta, and another source is from the data or the likelihood function. In this case, we're using a binomial data model, so it's from a binomial, and then posterior you'll be able to summarize in this way. And you notice in the table that I just showed, I have the success and failures columns. So we know that it's pretty straightforward if we're thinking about the likelihood, right? Because for the binomial likelihood, if you have Y success out of N trials, then the number of failures N minus Y, right? So you can list it, I mean, that's just what the data tells us. And this actually gives us a hint or like a suggestion as how we can think about the prior distribution, especially think about the information that the prior distribution can carry. So previously, when I said that one way you can select the priors, use the beta select function, right? That's where you specify two quantiles that you can think of, and then use that function to help you to select the value of A and B, right? Another way to select a prior is through like the table that I presented over here. Now you can think of prior AB, which is the beta AB, which is the prior distribution, in terms of prior success and prior failures that you guess what you should be. Okay, so earlier we said you can use the beta select. Now we're talking about, yes, a priori, if I don't see any of the data, now I'm just guessing, say, because this is a question about like the like percentage of people who prefer going out for Friday, right? So before seeing the data, if I think, okay, I guess maybe 60% of the people might choose Friday over any other day, right? So then if suppose, so of course, I mean, if you just say like a percentage in this way, then there are all kinds of setup of ABs that I can think of, right? So if I only want, like say, I want 60%. So the smallest number I can do if I want to do a whole number is A equals to 3 and B equals to 2, right? Because that's 3 out of 5, right? And so that means I can do, this is just a demo, okay? And that's representing my prior belief, right? But of course, if I multiply both A and B by 2, I can get the same prior belief, right? Because it's 60%. So another one we can do, and then you can have infinite number of ways of doing this, obviously. If you don't restrict yourself, even if you restrict yourself to integers, you can keep going to infinity and it's unlimited. And so this is definitely like a way to think about it. But as you can see, if I have two set of A's and B's in this ways, they're gonna give me different posterior distribution, right? And obviously they're gonna be different, so I wouldn't have the same inference outcome, even if I sort of have the same prior belief, okay? So another key aspect of thinking about the prior distribution this way is what we call something called prior sample size. Okay, so sample size we know, especially if it's in terms of the data, like the middle row over here, we know that like the data size is 20, right? That's how many surveys were conducted, and then 12 out of 20 is how many people chose Friday over the other days. And the prior sample size, especially in this setup, you can think of as the sum of A plus B. Okay, let me explain. So earlier, when I set up the two ways of AB in this way, I said that both of them represented, I think, 60% of success and 40% of failure, right? But then I said, yes, once you have different ways of setting up, you can have infinite number of ways of getting this same prior belief. However, they represent different prior sample size. Okay, so in general, the larger the sum of A and B, the stronger your prior belief is, and then that conveys as a larger prior sample size. Okay, so if you think about this, let me use a different color over here. So you see the posterior, it's gonna be this. And we know that if the data sample size is fixed, meaning that y is fixed, n minus y is fixed, then A and B will contributing obviously to the beta posterior. And then in general, the larger the A and B is, or both are, or the sum of them, the larger the contribution of the prior to the posterior, right? So that's why it is two aspects, okay? One of this is, okay, through A and B, how can I express my prior belief? And then through the sum of A and B, I can express how strong my opinion is a priori. Okay, so this is, again, another way to express your prior, and then you might want to experiment with different things. And in the setup that I introduced earlier for the demo, we chose A and B from a different approach using the beta select function. So now like A and B and fixed. But if you think about A and B in terms of prior successes and prior failures, the counts of them, and then A plus B is the prior sample size, you might have another way to express and then to construct your prior. And then of course, with different set of A and B, you're gonna come to a different set of posterior, which is A plus Y and B plus N minus Y. And then that will affect your outcome. Yeah.
I think so. We talked about earlier how, like, in this style of inference, your data is in the long run more important than your priors. But, like, for example, in this case, if in each case, like, your data sample size, your n is much smaller than your, like, the size of your priors, won't it get masked, like, no matter how many times you do a sequential update? Like, I'm just wondering what the tension between, like, the size of your prior and, like, the size of your sample.
Yeah, okay, so good question. For this case, I guess it's hard to, yeah, so when we talked about it previously about the size of the data and then how in the long run the data are going to dominate, especially through the sequential way, or if you just have a large sample size to start with, then I guess back then I was trying to convey the idea in theory that's what should happen. And then for this case, for the particular beta binomial update over here, I don't think I can give like a definite answer in terms of what exactly will be the tension, but it will be something I think interesting to explore, especially now we have like say the update procedure, especially here we know exactly what the posterior distribution is. So yeah, I don't think I can answer it, but I have the general I guess the general approach and direction of what it is, okay? And I guess I was a little bit absent-minded because I realized because I muted that and I didn't mute this. So whatever I say, not going from there this time, but from here. So next time when you ask, I probably just have to walk over so your voice can be recorded better. Sorry, I was listening, but then I just all of a sudden realized when you start speaking. Okay, yeah, so, okay, so I don't think I answered that question, but it will be something interesting to keep in mind. And then all of this are sort of like hypothetical situation. And then I mentioned those ideas about like sequential update as well as the strength of the prior and how much prior and data will be able to dominate. I think it's good seeds to plant in your head when you're thinking about your project or later on when you're doing exercises related to those aspects of the inference, okay? Okay, cool. So this is a good, I guess, intro over here about what else you can do if you want to specify a prior. And before we go into what I said, the actual derivation using all of the constants, I want to demo really quick if you want to use ROR Studio to compute and plot the posterior together with the prior. This is not using, this is still using the teach-based package that if you say over here, you see that I set up the AB, that's just a vector, right, with the prior numbers, the prior parameters. And then I also set up a y, that's just yn minus y. This is short for that. It's the vector of the the data success, information of the success and then failures, and then I can just add them up because of the table that we saw earlier, right? And then we have this AB as the vector recording the two parameters for the prior, and then AB underscore new is the vector storing the information of the posterior. Then using this beta underscore prior underscore post, we're able to draw this two, prior and posterior together. If you fit in the syntax like this, then you're able to plot them together. And then again, there are certain things we are able to talk about based on this plot, right? Okay, so let me bring up a couple of questions I thought about that would be useful to think about the comparison. So two things. A lot of times when we talk about a distribution, like the simplest stuff that we talk about, one is about the mean, the other is about the variance or the spread, okay? So let's look at the mean, which is the discussion question number 1 over here. I'm telling you that the mean, prior mean is 0.544. You can compute it because it is a beta distribution, and the beta distribution, the mean is A over B, okay? So you can get that number. And the posterior mean, obviously, I can also get that number. It's going to be A plus Y over B plus N minus Y, because this is how the theoretical mean of a beta distribution is. So I tell you this two together over here, and recall that the sample mean is 60%, 0.6. So how do you understand now the prior mean and the posterior mean? Like compare them, and then what do you think why, say, posterior mean is shifting larger towards the larger side? And then the other thing to talk about is number 2 over here, compare the spreads of the two curves. That's talking about the variability, okay? So I'll pause for 1 to 2 minutes. You can talk to your neighbors about it. And yeah, keep those two questions in mind, and then we're gonna bring back as a whole class, okay? And remote students, you can type to each other if you want. And
Yeah, like I said, yeah, that's I'm thinking of I mean,
what do you think? What about the mean? Well, the posterior mean is sort of like an average between these two, right? It's somewhere in between. It's going, I guess, further closer to, I think it's closer to the sample mean than to the prior mean, okay? And that's not surprising because the posterior is some kind of combined information of the prior and the sample, okay? So I will also demo in a minute as well how to break down the posterior mean to see that it is actually a weighted average of the prior mean and the sample mean. So that's important to know. Before I do that, what about the spreads of the two curves? When I talked about spreads, it's just the variance, okay? So the blue one, I think, has a higher variance if you think about the spread, right? What does that tell us? What do you mean by in the data?
In the distribution.
Yeah, in the distribution, right? So the blue one, which is the prior distribution, has a higher variability, whereas the posterior, so there are two distributions for the same unknown parameter, okay? So that makes it comparable. And then the reason, if you look at it, that the posterior is having a smaller spread, you can think of it as how the data is really helping us to sharpen our belief, okay? When we start with, we have really no idea, even though we use what the beta select function to represent as much as we can, but then it still overall has a sharper, I should say, like a wider spread, meaning that we have higher uncertainty about our belief of this unknown parameter. But now, combined with the data helps us sharpen the belief, and then the sharpened perspective is pretty much, you can see it from the narrowing of the spread if you compare the posterior distribution to the prior distribution, okay? So the effect of the sharpening is harder to quantify, but soon we're gonna do, at least look at part one over here, how the posterior mean is a weighted average between the sample mean and the prior mean, okay? All right, so that's what I thought I will do. So I will now, give me a second, pause it and then start a new part. I think that's what I do. Okay, yeah, so the new section that I want to insert over here is looking at how to actually, two things. One is to derive the actual posterior distribution. So earlier, I sort of showing you that, yes, if you just put every constant into the proportional sign, you only care about the terms about p and 1 minus p, especially about the powers, then you can arrive at a beta distribution, right? But there's no, I mean, I think by doing that, I don't think it's totally convincing that in the end it will be a beta distribution. We just know that it looks like a beta distribution based on looking at those terms. So, so now I want to demo how to do that more rigorously through a derivation. And then also I will talk about how the posterior mean is weighted average of the prior mean and the sample mean. So this, I think, overall can help you understand the model better, and then the Bayesian inference procedure a little bit better as well. All right, so I will start, and then I will give you some time to try it. So remember, we have a prior. I'm using the most generic way of writing it. So the prior, and then the likelihood. The likelihood is from the beta, from the data, which is a binomial. Okay, so this is what we have, okay? And the goal, remember, is try to derive this distribution, okay? And we already know the answer, so let me just write it out over here. What is it again? It's plus y, yeah, and then b plus m minus y, okay? All right, so this is the goal, how to derive this more rigorously. And one thing is, if P follows a beta distribution, then the density will be, this is just from the density of a beta distribution, okay? So we have, it's P raised to -1, and then 1 minus P raised to B minus 1, right? And then the density, which is now the likelihood function from the data, is what? N choose y, and then P raised to power of y, and then 1 minus P raised to n minus y. Okay, so this is pretty much where we started earlier as well, except before, soonish, we start to throw away those constants. Okay, but now let's keep those constants in here, and you can still arrive the same results, just with a little bit calculus exercise over here, right? So I will start for you, and then I will ask you to continue before we bring back as a whole class. So remember, we use this pi. Let me actually close this windows so it's easier. Okay. Yeah. So I use this pi, and then p given y as the notation for a posterior distribution. Okay. So what should we have? Using Bayes rule. We talked about using Bayes rule. So on the top, what do we have? The prior times the likelihood, right? In the bottom is the same thing, except now I have to integrate out the unknown parameter. Okay. All right, so I will do the next step for you. It's a little bit tedious, but you don't have to copy like one line. I mean, you can actually do it by yourself. I'm doing it in action, but it's following whatever we have set up so far. Okay. So I have the prior, which now I keep the constants. And then the likelihood, I keep the constants as well. Right? Yeah. In the bottom, it's tedious, but just for completion, I'm just copying and paste whatever is on the top, except now I have to integrate them out. Right? Okay. So I'll do one more step for you and then give you a hint and I'll let you think about what you can do to actually arrive at the conclusion. So what I want to show you first is, yes, we have some constants in here. We are keeping them, but we're actually able to cancel them out, some of them at least, okay? So here, because the integration is integrating over p, right? So this term and this term, they are constant, right? So they can at least come out from the integration sign, okay? And once you do that, they got canceled out with the top terms, okay? So I mean, because of the space, I don't want to like keep writing furthermore, but at least get that idea that because they are constants in terms of p, so they're canceled out. So what do we have now? We have, so let me combine the powers for you. So again, the top is very similar to the bottom, except that in the bottom, I have to integrate out p. Okay. I think we're all okay with this, right? Okay. All right, so the hint, I will give it to you. So obviously on the top, there's nothing more we can do. It's more about the bottom, what we can do. So you might not be realizing what you see when you see the bottom, what we can do. But keep in mind that a beta distribution is a proper distribution. That means, let me use a different color. That means if you have a beta distribution, say a PDF is P, it's proper distribution because it's going to integrate to 1, okay? And the range is what? Because P is a proportion, so it's from 0 to 1. So what's hidden over here is 0 to 1 as well. All right, so because of this fact, and now I'm also bringing your attention back to the top right, where we have the generic beta density. Okay, so if we think in that term, what do we have? That means if I integrate from 0 to 1, and then if I have a beta AB, that means if I integrate over P, it's going to be 1. Okay? This is not yet what you need. I mean, it's very close to what you need. So I'm using the prior as a demo of what we mean by this proper distribution that it integrates to 1. Okay, so my hint for you is, okay, this is a, let me use a different color. This is a constant, right? This is a constant. So if I now want to integrate over p with some powers, p and 1 minus p, with some powers, I can immediately come to this conclusion. This is generic, okay? It should be 1 over the constant on the left, right? So this is generic. I'm not saying that this is exactly what you need to use, but this is good hint for you to think about what you can do for the bottom over here, okay? So the bottom is a different beta. On the left, what I just did for the demo is a generic beta AB, okay? But now we're not integrating over p raised to a minus 1 and 1 minus p raised to b minus 1. We're integrating over p to the power of a plus y minus 1, and then y minus p to the other power of b plus m minus y minus 1. So use this hint, because obviously we can sort of recognize that the bottom can be integrated to some constant, okay? And the way that we can do the constant is trying to recognize the powers. And the powers gonna be coming from a posterior distribution, okay? So I will pause for a few minutes to give you the time and space to think about this. And this is, some of you might think, okay, it's not important as long as I know what the posterior is. But again, I think this really helps us to get an idea of a Bayesian inference procedure. I mean, this is the simplest case. Later on, you will see that it gets much more complicated if you want to derive the exact distribution. But for now, we want to get very thorough about this beta binomial conjugate. So later on, we're able to convince ourselves that we only need to care about the kernel, but not the constants, okay? But I want to convince you that the constant procedure does work, and you just need some practice, and then you need to be familiar with the integration task, okay? So I'll give you a couple of more minutes to try it, and I will do the demo on the screen, okay? So I will leave as it is, so you can draw ideas from. But when I demo, I will just erase everything and start from scratch, okay? If you get some ideas, you can talk to your neighbors and show what you have done or what you're stuck with. And yeah, feel free to talk. Oh, hi.
Yeah, it's one over. So it's all is divided by 1 over base. So that's it. So it's not actually that, like, this is the first one, everything you have that translation. Yeah. So you're gonna ask that. Yeah. Actually, the fact of what he's doing is not what I'm doing. I don't know what he's doing. I'm doing this. I just something else.
Okay, so I did some writing on the left, and I was just following the hint that I provided to you earlier. So let's see, we have, this is what we need to evaluate, right? And then we recognize that the kernel is very much like a beta. And if we utilize that information by recognizing the powers, we are able to say that we do have this as given, right? This is just, if it's a beta distribution, and in particular, it's going to be a beta a plus y, and then b plus n minus y, right? So because this, so what's in the integral is exactly the PDF of this beta distribution, and we know beta is proper, so it should integrate to 1. So we know that we can use this information and then know that this integral, the one that we want to evaluate in the bottom, in the on the right hand side, is going to be the reverse, I should say the inverse of that constant. Okay, and then we can actually use that because it's exactly that value in the bottom, so we're able to show that the posterior distribution of p given y will be p to a plus y minus 1 minus p time to the power of b plus n minus y minus 1, and then divided by that constant that we computed, right? And once you flip it up to the bottom, to the top again, you can see that the posterior distribution, the one that we derive, is again going back to what we just used, okay? But we didn't throw away any constants, right? We now have the exact distribution, the exact expression of this posterior distribution, and then it is exactly a beta distribution, okay? With 2 parameters, a plus y, and then b plus n minus y, okay? So we sort of previously hand-wavy doing this, just throwing away all of those constants, but in the end, as you can see, it's really just that particular constant we're playing with back and forth, okay? And then in the end, it's not canceled, and it's super useful actually for us to help us to recognize that this indeed is a beta distribution, okay? Cool, so this is definitely a good, important exercise, I have to say. that for you all to get the sense of how Bayesian inference is done, in this case for a continuous model, or a continuous random variable, unknown random variable, because now we're doing integration in the bottom, okay? All right, so this is the first part that I want to demo using a whiteboard. Another part is what I said earlier. Remember, let me bring this back really quick. That the discussion point number 1 over here, we talked about it earlier, that the posterior mean is somewhere between the prior mean and the sample mean, okay? But exactly how is actually given if you have this beta binomial model that we just talked about. And let me now show you how we can see that the posterior mean is a weighted average of the prior mean and the sample mean, okay? So let me first write down what we know. Prior mean. So this is property actually of a beta distribution. So if you have beta AB, then the prior mean will be A over B. Okay, so it's just the prior, sorry, I should say the mean of a beta AB is just A over B. Okay, that's just features of a beta distribution. What's the sample mean? It's the sample proportion, right? So it's Y over N. Okay, so if you have a binomial NP and your outcome is Y, then this is your sample mean. Posterior mean, what do we have again? We have beta A plus Y, and then B plus N minus Y, right? Yeah, so it's a beta distribution, so we know it is what? A plus Y over B plus N minus Y. Right? So think about how you can, and pause for 1 minute, think about how you can actually break this down into something that we're able to recognize. Oh, I made a mistake. I'm sorry, guys. Oh, bad practice. So yeah, sorry. The mean is A over A plus B. I'm sorry about that. Yeah, for any beta distribution, my bad. So I will start to realize, no, I'm not able to recognize what this is. So I guess I did made a mistake. So so for any beta distribution AB, the prior is A over A plus B. Okay, so that means the posterior mean is A plus Y plus B plus N minus Y, which if we cancel it out, sorry about this, should be this, okay? All right, so how can we show that the posterior mean is weighted average, right? So let me do a couple of steps for you. You can also just do it by yourself. It's again some algebra exercise. So one thing you can do is to, let's see, what can we do? How can we put it into some form? Okay, so I did it. I mean, it's not actually too straightforward. You sort of have to work back engineering backwards. But if you tried it, you will realize that if we have the posterior mean in the expression as a plus y divided by a plus b plus n, we can actually break it into two parts. And each part has, like one part has the prior mean, the other part has the sample mean. And then for each of the two parts, we also have something that we use as the weight when we're talking about what we say weighted average. Okay, so this two, I mean, the way that you can do is because those canceled out, and then you're gonna get the same, the left-hand side to be the right-hand side equals to the right-hand side. But it's important to keep them in the way that it is, because first of all, you can see that if you have a prior weight in this way, which is a plus b over a plus b plus m, that would be the weight that you use for the prior mean. And then if you have the sample weight to be m over a plus b plus n multiplies with the sample mean, you get to the posterior mean, okay? So when we talk about, I mean, this is not arithmetic average, okay? This is weighted average because you apply different weight, okay? And another important feature of this is that the weight, two weights should add up to 1, okay? And they do, okay? It's a plus b plus n over a plus b plus n. It is 1. And one more thing before, I mean, this is, I guess, straightforward to read, but another important thing, I think, which can help us to link what we talked about as the prior sample size. Remember I said that a plus b can be considered as a prior sample size when you're trying to specify your prior. You can see it even more clearly here. Because if you look at the two weights that we do, I guess if I further just bracket them together, it's easier to see. So you see that the total is a plus b plus n, okay? And the weight from the prior mean is a plus b over the total. And then the weight for the sample is n plus n over the total, okay? And the total, remember, n is what? N is the sample size, right? And then we also talked about the idea of using a plus b as the prior sample size. So think about the total sample size as the prior sample size plus the sample size, yeah? And then you will see that the weight that you get for the prior is exactly the prior sample size over the total sample size. And then the weight for the sample is the sample size over the total sample size, okay? So if you're if you have seen this kind of weighted average idea before, you will know that the weights, no matter how many you have, in this case, we only have 2. So this 2 should add up to 1, okay? And then again, I think this way of looking at the weighted average for the posterior mean helps us to reinforce the idea about the prior sample size that we talked about, okay? So prior sample size, again, in the past, when we talked about it, it's more about how we're gonna use our prior belief, thinking about A and B as prior success and then prior failures, right? And then we talked about what if A equals to 3, B equals to 2, that would represent the same idea as A equals to 6 and B equals to 4, because it's what, 60% of success, right? But then we saw it before that, and we can see it over here as well, that if you have different values of A and B, you're gonna come up with the same data. You're gonna come up with different posterior, right? So in addition to think about the actual values of A and B, you might also want to control their magnitude, because you don't, I mean, if you have really strong opinion a priori, then you might, yes, I want to contribute more from the prior, then you want to have a higher magnitude of A and B, or A plus B in particular. And whereas if you don't have very strong opinion, you might want to use very low information over there. And that can be conveyed as a smaller sum of A and B, okay? And now thinking about the posterior mean, we can even see it more clearly that the two weights are exactly conveyed from the prior sample size and then the data sample size, okay? So earlier, I think, so if we keep this in mind, that the two weights that we have over here, let me try to see if I can bring this back really quick. Oh yeah. Oop, boop, 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 boop. Okay, that's a little awkward, but I do want to show you. Let me just erase. Thanks. Never mind. I do want to show you here. Oops. Just give me a second. Okay. I do want to show you here that these are the means. These two means are just from the beta distribution. But you can summarize throughout the way. Say if you make 1,000 draws from the two different beta distributions and just summarize the empirical mean, that would be very close to these numbers as well. But again, as you can see that this data overall is what is, I mean, the mean, posterior mean is sort of closer to the sample mean, right? And it's not surprising because A and B are pretty small when we select them. One is a little bit over 3. The other one is about 2.5-ish. So the sum of A plus B is what, 5.5. Whereas what we have for N is 20, right? So it's not surprising that the data is dominating when we're doing Bayesian inference, I mean posterior inference for the P, and then it's not surprising how it's reflected in the posterior mean, because we saw that it's a weighted average, right? It's again, the two weights are this, okay? And this one is larger, okay? Because of the way that we set it up. Okay? So keep all of those ideas in mind, like prior sample size, how you choose a prior distribution. They are pretty useful in not only making the actual inference for your application, but also just collecting all of this and keeping all of this in mind when you are and trying to understand how Bayesian inference is done and how actually the prior and the post, I should say, how the prior and the data are jointly contributing to the posterior. Okay, cool. So this is what I want to talk about. Let's see, for this part, and we don't have much time left, but I do keep doing. Yeah, we don't have much time left, but I do want to at least talk a little bit about different ways of doing Bayesian inference with continuous prior, and whatever is not done today, we're gonna carry over on Thursday. Okay. All right. So one thing you can do, just like what you do in frequentist approach, is you can do hypothesis testing. Okay. And Bayesian hypothesis testing, this is a simple demo. Suppose one of the Tokyo Express's workers claims that at least 75% of the customers prefer Friday. Is this a reasonable claim? Remember that when we come to a beta posterior distribution for this P, we are able to summarize it, right? Because we know exactly what the distribution is. So we can actually sort of compare it against to this claim, whether, or like say, at least we can look at the probability of, like come up with a probability statement about P is greater or equal to 75%. Okay, so what can we do? You first of all find the posterior probability that P is greater or equal to 75%, and then you can make a decision based on the value of this posterior probability. And again, this probably is a probability statement. Okay, so you are able to, I guess, make decision based on this. And then if the probability of that event is small, then we're gonna reject the claim. Okay, so the way to do it, there are various ways. I'm just gonna demo one thing. If you want to use the teach-based package, you can do this beta area. Okay, so you can try it later on. So notice here that these two are the posterior parameters, okay? Because now we're summarizing the posterior distribution. Okay, this is one thing you can do. And if you're already pretty familiar, and by the way, when you do it, the probability is pretty small, right? So this is saying that the probability that P is greater or equal to 75% is about 0.04. So this is really low probability. And so it's not really supporting the claim of this worker, okay? So this is one way you can do it. If you're pretty familiar with R, you might know that, like, so for beta distribution, you have 4 different functions that you can use in R, right? R beta, let's say D beta, that's evaluating the PDF, okay? Q beta, P beta, and then R beta, good, yeah. So I personally always mixed up the middle two. So it's definitely one of this will be able to give you the quantile. I don't remember at the moment, sorry. But now what we're trying to do is we try to find the probability that this random unknown P is greater or equal to 75%, and we know it is a beta distribution with its 2 parameters. So you will be able to use, I think it's Q beta to get the to get the value that what is the probability that P is greater or equal to 75%. Okay, and you should give a very close result to what you can use with the beta area function here. So that's another way you can do it. So I encourage you to try it later, just to practice and then verify the results. Okay, so this is what you can do for doing it. And this again, this exercise, I put it over here. You can do it afterwards when you're using your laptop, because I notice not everybody is using it in class. That's totally okay, but I do insert this exercise. And then if it's trying to evaluate the claim that at most 30% of the customers prefer Friday, you're just reporting the posterior probability of P less or equal to 30%, right? And then evaluate how large it is. Okay. So right now we're not doing it super rigorously. Like, I'm not saying there's a threshold that if it falls below it, you're going to reject. We don't do something as very strict as what frequentists usually do, but it is a proper probability statement that we're trying to make. And if the probability is low, then you probably won't believe it, right? So that's the general idea of the Bayesian inference. Okay. All right, so I would do this credible intervals, and then we're gonna call it for a day. So credible intervals is something like you can think of as the equivalent of the frequentist confidence intervals, but credible intervals over here, it is again, I shouldn't say again, it is a interval that once you come up with the interval, you can say that with certain probability that the unknown parameter are gonna fall into that interval, okay? Recall that in the frequentist approach, when we talk about credible interval, it's the other way around, right? It is, if you do this experiments for a fixed number of time, a large number of times, and then say if it's a 95% credible interval, it's gonna be 95% of those intervals gonna cover the truth, okay? Whereas right now, because now we're making probability statement about the unknown parameter. So if you can come up with the interval, we call it as a credible interval, that is just going to show you your confidence level. It's going to be a probability statement about the uncertainty, okay? So a 90% Bayesian credible interval, just going to be an interval contains 90% of the posterior probability, okay? It's a probability statement. So you can do beta interval in the beta teach base function. You can do that, and then if you do it, then you can see that the middle 90% credible Bayesian credible interval is between 0.43 and 0.74. Okay, so that's 90% Bayesian credible interval. It contains the middle 90% of the posterior probability. It is the middle one if you use this function, and you can also do, like, say, in the same package using the same function. As soon as you change those values to 98%, for example, you will be able to get a 98% credible interval, okay? And you can also do this from the, I think it's the p beta function that embedded in R, okay? So those, again, because what we're doing is getting like the quantile over here. So as soon as you know the exact distribution, which is the beta 15.6 and 10.56, you're able to summarize just based on that. Okay? So I think we're gonna call it a day for today. And on Thursday, when we come back, I will talk about Bayesian prediction. And then I will also talk about some other computation aspects of this approach, okay? All right, and don't forget that Thursday homework 1 is due, so just print it out the cover page, staple everything together, and bring to the class, okay? I have office hours today and tomorrow if you want to stop by. All right. Thank you, Haley and Elliot. Bye-bye.
Bye.